Earth science time. We're going to talk about, what should we call it?
Drifting continents.
That's beautiful. Let's call it drifting continents. I remember, are you all juniors? Yep. I remember teaching you guys about this, so I know you have this information, or I know you have had this information from when you were in 8th grade, but we're going to review this a little bit. A man, you might remember him. Do you? I can tell if you remember him because I'm going to have you say his name. What's his name?
Alfred
Wegener. Yeah, you do remember. Alfred Wegener was a German scientist, well, by the time you call it a naturalist, but a German scientist in the middle to late 1800s. And he had this idea, it had been observed for centuries, that things like, as soon as the first semi-accurate maps of what was then called the New World, right, the North and South America, as soon as the first semi-accurate maps of those came out, people realized, it looks like what? What you just did your lab on. It looks like, yeah, it looks like South America and Africa fit together, and that kind of Europe and North America do. And so it was, people probably at the time, I don't know what they thought because I wasn't there, but people at the time probably thought, like, what an interesting coincidence, right, that they look like they fit together. But Alfred Wegener kind of took it one step further, and he tried to gather evidence that not only did they look like they fit together, but that they at one time had been together. And do you remember the pieces of evidence that he used? Evidence for what we call continental drift. First, let's define this continental drift real quick. I'm not going to write it up here because you should already know it. But what's continental drift? It's the idea that what?
That our continents once used to be joined.
Yeah. The continents specifically, in this definition, the continents specifically move over the face of the globe. You can see how this would be upsetting to someone. In fact, this was not, unlike many of the things that we study in like physical science and biology, this was not accepted widely at all until like the 1960s. Like this was not very long ago that people didn't buy this at all. And you can see probably why. Like there are geologists alive today who remember times when this was not an accepted idea. And why wouldn't it be? Like what would make someone upset about someone telling them this is the way it is? Right, because it seems like, I'm standing here, I'm on a continent, it doesn't feel like it's moving, right? That's the kind of evidence that people would say as rebuttal. Like, we don't have, at the time, they would say, we don't have evidence that the continents do move, right? And it doesn't seem like they do, because, you look at a map from the 1600s, the age of sail, and it looks like a map from today. And that's true, but there are two reasons for that, right? Why would a map from the 1600s look like a map from today?
Because
it moves so slow, and also that map from the 1600s, it's pretty, but it sucks, right? It's probably not super accurate. It's not down to the meter even of accuracy. And even if it was, the continent has, maybe they've moved a meter apart in that amount of time. It's so slow. So he had this evidence for continental drift. Do you remember what they were? We had three things.
continents look like they fit together.
Yeah, that is one of them, but that's, as we said, that wasn't his evidence, right? And it's, at the time, cartographers thought that because it might just be a coincidence.
Fossils on
There you go.
two ends.
Fossil evidence. And so what he did was he found, what was the name of that thing? Glossopteris, which was a plant fossil that he found, if I remember correctly. There were two fossils, I'm getting them probably confused, but Glossopteris he found in southern Africa and southern South America, which now are separated by an ocean. And it's a dang plant, right? That little boy did not swim across the ocean, I'll tell you that much. So he thought, this plant developed in the same area, right? Because all the plants that we see today exist in the same area as other types of that same plant. And so he sees this Glossopteris, and it's over the spread of these continents, and he thinks maybe the continents, when this thing was alive, were one time together. There are other fossil evidence. Glossopteris is the one I remember, and like I said, I think it was South Africa and southern South America, but it may have been something different. What was the other one? There was fossil evidence, where he found the fossils that were the same on multiple continents. Do you remember another one?
Wasn't it like the plates or something like that?
Well, it was the rocks that make up the plates, so let's talk about rock evidence. The one I distinctly remember about this from, and I'm not even sure your current book that we're reading out of now mentions these, but this, yes.
Climate
it does.
evidence?
Yeah, but first let's talk about the rock evidence. You're right, I'll write it down. Climatic evidence. let's talk about the rock evidence first. The one that's really striking to me that I remember very well is that we talked about rock types earlier in the year, and it wasn't just that granite as a rock was found in these two different places, but the exact same type of granite with the exact same minerals, the exact same composition was found in Scotland and in the Appalachian Mountains in North America, right? And so the fossil evidence, they were like, the plant doesn't swim across the ocean, but maybe for some reason it spores it, right? So that can kind of be waved away if you really don't want to buy it. But the rocks did not in any way spread across the ocean, right? So this is very good evidence. It's the exact same kind of rock in both Scotland and in North America, which as you know now are separated by the Atlantic Ocean. So there must have been, at some time, those must have been together.
Scotland and what?
Scotland and North America, the Appalachian Mountains. If you want to know how to spell Appalachian, I'll help you. I spelled it wrong. Don't look at me. Don't look at me. I can find it in here. I spelled it right, actually. Let me try again. Oh, now I've forgotten. I'm embarrassed with myself. Appalachian Mountains. And then I'm going to put, the mountains in Scotland are called the Caledonia. So the Appalachian Mountains, you know where they are. They're where the hillbillies live. And the Caledonia Mountains are in Scotland. And the climatic evidence, what evidence might we have of the way climates used to be?
What kind of, like, plant fossils?
It's still fossil evidence, it's just that these relate to the climate. So in this case, we find in his examples things that we know prefer a tropical environment. We find in environments that are now non-supportive of that. Like we might find palm frond fossils in Antarctica, which we do find. And obviously Antarctica has not had a palm tree for a long, long, long time. And so the evidence here is that Antarctica must be in a different location relative to where the equator is than it was today. So all these things together, he spent his whole life moving around the globe looking for these things. And in his lifetime, but it was not widely accepted that any of this was true. But now we understand that these things are really great evidence. There's no other explanation for these, or at least no other parsimonious explanation for these. Yes, Tylee?
So, you said that they move really slow apart. So, do you think, what kind of plant did you say was in Antarctica?
I guessed palm frond. I know there are palm
Yeah.
fossils found in
So-
Antarctica.
Don't you think those would have adapted? Like, do you think there's any plants that,
Probably. So,
because it moves so slow,
you're right.
they would get some
and maybe they could for a while, but now we know there isn't plant life at all in Antarctica. And so we find any kind of plant life fossil there. We know that the climate must have been at least somewhat different. At least when I say plant, I mean like large scale plant. Like there's
Yeah.
photosynthetic algae that we could
Right.
consider plants, but they're not like, oh, a little bush,
Oh, grass.
Grass. Right, not even grass. There's a, look at the picture on page 472. You can look this up on YouTube if you're watching this. It's a picture of Alfred Wegener, and this picture makes me sad. This is the picture of a man whose entire life work has not been accepted in his lifetime.
Oh.
472. It says 1930s, so really I was a little bit wrong. I said late 1800s, middle to late 1800s. I think it was more like late 1800s to early 1900s, but
So he didn't get to die to see that his stuff was right.
Right.
Oh, well.
he didn't get to die.
Yes,
He did get to die. He did get to die, but his stuff was considered wrong at the time. We now accept it, right? And we realize that he was a pioneer in this work, but
He has some pretty cool pants.
look at them cool pants though. He's got some fur pants.
Oh, yeah.
So you know what? That's the moral of the story. Even if your theory is about to get rejected by the entire science,
Wear fur
you
pants.
got some sweet pants.
And his boots.
Okay, let's stop.
At least
analyzing
that's
this
right.
now. Those are cool pants though. Let's all get some pants in solidarity with Alfred Wegener. Okay, we're going to move on now and talk about some more modern. So I want you to be aware, these are the evidences that Wegener himself could collect and did collect, and these are very supportive of the idea of continental drift. I want you to make sure that you have this differentiated in your mind from plate tectonics, which is a separate thing. Continental drift is referring specifically to what? The continents, right? That's why it's called continental drift, whereas plate tectonics applies to the whole Earth's surface, right? And so we're going to move on and talk about that next. So plate tectonics. You know about the word plate? Flat thing. I don't know. Flat thing. A metal
Like a
plate
plate?
is like a flat thing. We're not going to talk a whole lot. We've already talked way too much about the word plate. You know what the word plate means. Tectonics, this word, have you ever seen another word that has this little root word, tect? Have you ever heard of an architect?
Oh.
An architect is someone who designs, say it, buildings. Buildings, yeah. So this tect is the Latin, related to the Latin word for building. So we can think of these as the plates that do what to planet Earth? Build, yeah, they're the building blocks of planet Earth. So this idea is that, well, I'm not going to write this one down either. Well, I don't know, I already have the equal sign, maybe I should. It's the theory that Earth's, you fill in the rest. You fill in the rest.
It's a theory that Earth's made of
Earth is made up, yeah, I'm going to say Earth's crust
crust
is made up
of constantly
moving plates. Yeah, this is beautiful. Excellent definition. Have we, in Earth Science yet this year, talked about the lithosphere and the asthenosphere? I think we did a little bit when we talked about igneous rocks, but we're going to talk about it again because Levi said no.
Theory that,
This was supposed to be a circle, but I had to move to get around so my hand didn't bump into my whiteboard spray. This is sweet Earth. You have, since you were very young, seen a diagram of the inside of planet Earth, right? You know
yeah,
about
we
it.
used to have a leak.
What's down here? I do it as a hemicircle.
Core.
Little core.
Is that inner or outer?
We're just going to call that the core because we're not really terribly worried about that part yet. And then there's this whole goopy mess in here is called the what in general?
Mantle.
Mantle. And then we can just say that this line that I drew is the
Crust.
crust. And this is a very nice, it's not inaccurate, but it's a nice simple definition that you can tell the elementary school kids and they're like, mantle is in the middle, core is in the middle. Yeah, you know, they can just say all their little words and memorize it. It's a little bit more complicated than that, and what we're going to talk about is that there's this, we also use this definition more often in geology, where this part of the mantle that is solid and the crust we together call the lithosphere.
The what?
Lithosphere.
But what is it?
It's the part of the mantle that is solid and the crust. I didn't do a super hot job drawing my circle by the time I got over here, but you understand what it means. So the lithosphere is not just the crust, but also the part of the mantle that's solid.
How do you spell that?
Litho?
Is it L-I-T?
L-I-T-H-O. Sphere. What's sphere mean?
Circuit.
Yeah, it's a little like three-dimensional
So
circle.
it's the crust and solid mantle.
And the top part of the mantle, which is solid, yeah. Or I should say the nearest part of the mantle to the surface that is solid. And then litho, what's that mean? Remember the word lithify?
Liquid.
No.
Hard.
Yeah, it means rock specifically, yeah. So lithosphere is the part of it made of solid rock, right? And then beneath the lithosphere, most of the mantle is this kind of, it's always been described to me as like peanut buttery. Like it's not liquid like your delicious, nutritious smoothie or the water in your canteen. It's goopy, right? It flows, but it's also behaves as a solid when it's under pressure, which it is. And this whole thing is called the asthenosphere. This is related, this word asthenos in Greek means weak, meaning that it's not solid, right, in this context. So we have the lithosphere that is made of solid rock, and the asthenosphere, which is beneath it, which is made of kind of more fluid. It is still solid
Is it
rock.
like gooey?
Yeah, it behaves like a liquid because of what? Two things. Yeah, it has a very high temperature and it has a very high pressure. And so between those two things, it's able to move in a fluid way, and that's called the asthenosphere. Let's draw another little diagram. We love drawing diagrams. Yep, let's get that erased. Good job erasing it. I'm going to draw, this is going to be another cross-sectional view, but we're going to make it a little bit more zoomed in. So we have here, this is supposed to be a continent. This is supposed to be a continent. And this is the ocean floor.
Okay.
And then under here, what's under here?
Like a song.
Well, what's under here? If this is all crust, or we can say this is all lithosphere. Let's say this is continental. Let's call it crust. Continental crust, ocean floor crust, and then this is also continental crust. What's under here? Mantle, or specifically the asthenosphere. Mantle. So mantle's down here. And then what's above the ocean? crust, water, the ocean. This is certainly not to scale. This is definitely not to scale. This would be a really little squat, little super deep ocean. The ocean, this is the ocean floor crust, this is the continental crust. We have talked about this before, I want you to be able to remember it, but I don't know if you do. Do you remember what I said, that the continental crust is primarily made of what type of rock?
Oh.
Yeah, say it, granite. So this is granite, which is less dense igneous rock. It's still dense, right? It's still a rock, but it's less dense compared to what the ocean floor is made out of. What's the ocean floor made out of? What's the ocean crust made out of? Do you remember?
What did you start with?
B? BA? BAS?
Basalt.
Basalt. We'll talk more about how the oceans themselves formed later on in the year, but for now, I don't know if you've ever thought about that, but you might have wondered why are there oceans? Like, why is the water there? And the answer is that have you ever looked at the moon? That's a stupid question. Of course you've looked at the moon. Do you see on the moon there's like some white and dark patches? On early Earth, without water, if we were to remove all the water from planet Earth, it would look like that from outer space too. The white patches are these granite crust. The dark patches are the basalt crust. Because the basalt is a more dense rock, it kind of sinks into the mantle lower. And the granite is a less dense rock, and so it really does float above the mantle because it's less dense than the mantle. And so it's almost like if you have some delicious beef soup, right? And you got the carrots and potatoes and stuff that are floating at the surface, like the granite continental crust, and then the nice dense chunks of beef are sinking to the bottom, like the oceanic basaltic crust. And so then when you pour the broth over all of it, obviously the broth fills in the parts that are low, right? The basaltic crust. The ocean fills in the parts that are low because they're more dense. Does this kind of make sense? We'll get more to how the oceans formed later, like I said. But for now, you should know that the continental crust is largely granitic. There are other rocks in it, but it's largely granitic. And the oceanic crust is largely basaltic, which is why the oceans are there. What happens when, because of something we'll talk about in a little while, this is separating, right? We talked about this before. What happens when they separate? What's going to come up in there? What's going to get up in there? Yeah, some magma from the mantle. And as that happens, it cools right away because it's in the ocean. We even saw pictures in our video of some magma escaping into the ocean floor. And it looks for a second like really bright light, and then it's just instantly solid rock. Specifically, what kind of solid rock, if you had to guess? Yeah, igneous, but basalt. As this happens, when it comes up, and we talked about this when you were in 8th grade as well, so we're going to kind of glance at it, but as this comes up, remember this basalt is iron rich. Iron rich. We called it mafic, if you remember from chapter 5. Iron rich, mafic rock. However, the little atoms in the iron rich mafic rock are aligned, they align themselves to Earth's magnetic field, and they stay that way when they solidify. So if we look at this real close, we say that every little atom in the iron is like a little compass. And they all point to Earth's magnetic field, right? They all line up with Earth's magnetic field. You with me so far? So you get this little nice layer here of rocks that are... Yeah, exactly. And then after time, after about somewhere between 10,000 and 100,000 years, Earth's magnetic field switches. It's called a polarity reversal. And then the new rocks that are coming up are switched the other way, you see? And so in that way we get these stripes on the ocean floor.
How does that happen? I'm sorry, I was right.
When it's liquid,
Yep.
the iron atoms can align themselves with Earth's magnetic field, and they do.
Okay.
And they get locked in that way when they
Yep.
solidify. And then Earth's magnetic field switches, and so the new rock that's coming up has a different polarity. And so as this pushes out, every new little layer has a different polarity. Let's look at the, you can't do this online, but you can look this up. Look at the picture on page 477. On 477, you can see they've got red here for normal polarity and yellow for reverse polarity. Do you see that? They even have names of these magnetic eras. So look, the very middle one right now.
Gilbert.
They do have names. Some of the names happen to be Gilbert. But the red ones here represent normal, what we call normal. Why might we call that normal polarity?
What we're used to.
That's what it is now, right? Exactly. And the yellow ones are the opposite of what we're used to now. And so here's another piece of evidence, right? This is evidence of plate tectonics because we can see, we can literally go in.
So this doesn't happen in our lifetime.
It's constantly happening, but it doesn't. You mean it doesn't switch?
Yeah.
It actually is switching right this second. It's been switching
But
for the
it's
last
not
100
like-
years or so.
Right, but it doesn't.
It's not like one Tuesday. It's like and
Yeah.
you're like, whoa! No, people do things. In fact, I've seen actually on like CNN or Fox News, they're like, oh, the magnetic field is reversing. Your car's gonna flip upside down. No, that doesn't happen. It takes an awful long time, and it's really quite gradual. In fact, this is not what we were supposed to talk about. This is not part of this. But right now there are about 12 different, and there might be more now, magnetic poles on Earth. There's still, the North Pole is still stronger than the rest of them, and the South Pole is too, but it is in the process of switching. And it might take thousands of years, it might finish happening in 100 years, but it's not going to happen tomorrow, and it's not going to happen all at once. But it does happen, and we know it happens because we have evidence of it
So
happening
what's
in the
gonna
past.
happen when it happens? Nothing?
I don't know. There's some thoughts that maybe GPS systems will get screwed up or something, but it's nothing that will, at least in my opinion, it's nothing that'll like, your car's not going to flip
Your
over.
car will
No.
flip. God, Dolly's.
Do you have a question, Skylar?
Once Sean's
So it
ready,
doesn't
investing
affect
is-
anybody else.
It does affect a lot of stuff, but I'm saying that it'll probably be able to like, they will come up with ways that you can like,
Does it affect, the plates?
yeah, exactly, and that's what so we can see that it changes the way that these plates show up on a magnetometer. You should write that word down, magnetometer. You've defined this in your vocab. What's a magnetometer? It probably is a meter that measures what?
Magnetic?
Yeah, magnetic fields.
Can you say the word again?
Magnetometer. So using a magnetometer attached to a ship, we can tell that this has happened in the past. This is the closest thing to actually seeing plate tectonics occur that we have. Well, it's the second closest thing. There's another, even better way that we can see this happen.
So since it changes the direction of the tectonic plates.
Yeah, it changes the direction that the iron atoms are aligned in the tectonic plates. So you know, like if we had a regular magnet with a north and south pole, we can say the normal polarity ones are where it's like this, and then we can tell that the other ones are switched the other direction by using a magnetometer. The ocean floor wouldn't look any different to your naked eye, but it responds differently to a magnet in different areas. Before we go, the last thing I'm going to talk about, we will talk about plate boundaries and why plate tectonics occur at all tomorrow, but before I go, the last piece of evidence that we have, and this is maybe not even just in my opinion, but as a fact, the best way that we have evidence for this is that there are little GPS stations on every continent, and we can literally measure how far they move every year, right? So we know this GPS down to the nearest millimeter where it is, and we know where this one is, and we can tell that they're getting further apart year after year. So this is a way that we directly measure. Let me tell you, there is no one, at least no one who knows anything, who disputes this now, right? I told you that even in the 1960s, people were like, I don't know, Alfie, this sucks. But now, it's irrefutable evidence because we can actually measure, right? Saying that this doesn't happen would be like saying that flag isn't moving right now, because we can see the flag moving, right? In the same way, we can see the continents moving, we just need a special instrument to do it. Do you have questions about any of the evidence for plate tectonics? So like I said, today we did the evidence, Alfred Wegener's evidence, some more modern evidence, and then this cool GPS evidence. And then tomorrow we'll talk about how the plates move specifically and why they move. But do you have questions about evidence for now?